we have a sample question from our textbook, which is a Brown 10th edition. It's from page 737, in which we do an example of a buffer question where there's a partial titration. Whenever you have a partial titration with a strong base with a weak acid, for example, because only half of the, or a certain amount of the weak acid is used up, you get a combination of weak acid and its conjugate base in solution. Those are conditions for a buffer. So in this problem, we have 10 mLs of 0.05 molar sodium hydroxide being used to titrate 40 mLs of 0.025 molar benzoic acid. So what I've done here is calculated how many moles of each of the two species are present. When you add this to this, you'll see that the sodium hydroxide is half the amount of the benzoic acid. So what happens at the end is that you get that many moles of the benzoate ion appearing in solution. You also have to keep track of the fact that because you're adding 10 mLs to 40 mLs, the total volume of the solution turns out to be 50 milliliters, which is 0.05 liters. So we have to take that into account when you calculate the final concentration of the acid and the base. So that the benzoic acid is in excess. 1.0 times 10 to the minus 3 minus 5.0 times 10 to the minus 4. These are the actual mole amounts. It means there's 5.0 times 10 to the minus 4 moles of benzoic acid left. That 5.0 times 10 to the minus 4 moles is dissolved in 0.05 liters. So its concentration is 1.0 times 10 to the minus 2. So the concentrations of the two species, benzoic acid and the benzoate anion, end up being exactly the same. So when we enter these two numbers into the Henderson-Hasselbalch equation, pH is equal to pKa plus log of A minus over HA, we'll see that because these two numbers are identical, the log of 1 gives you 0. So the pH ends up being exactly equal to the pKa of benzoic acid. Same type of problem is done now where we reversed it so that the titrant is hydrochloric acid and the thing being titrated is ammonia. This time we have 10 mLs of 0.1 molar and 20 mLs of 0.1 molar being mixed. So the total volume at the end of the experiment is 30 mLs. We have 1.0 times 10 to the minus 3 moles of hydrochloric acid and 2.0 times 10 to the minus 3 moles of ammonia. So when that titration is completed, 1.0 times 10 to the minus 3 moles of ammonium formed. So the amount of ammonium is equal to the amount of ammonia that's left over. Half of this stuff gets used up. So these two numbers will be identical when it comes to the concentrations. I didn't even bother converting them to concentrations because they're both in the same solution. So the concentrations are going to be the same. If the mole amounts are the same, the concentrations are the same. The same thing is going to happen. The numbers are going to cancel out. So the pH is going to equal to the pKa of ammonia, which is 9.26. And the way I found, by the way, the pKa of ammonia was to use the Kb of ammonia, which is 1.8 times 10 to the minus 5, and I put it into the equation for the ion product of water. Kw is equal to Ka times Kb. So if you solve for Ka, Kw over Kb is equal to Ka. In this case, it's 1.0 times 10 to the minus 14 over 1.8 times 10 to the minus 5. And that's where I got this number for the Ka of ammonia. And then the pKa is 9.26. And as it turns out, pH equals pKa in this problem. The answer is 9.26.